In part 1 of this video, we looked at power functions and rational powers, and in particular we looked at this pattern here where n was not all of the rational numbers, but n as an element of the integers, so -2, -1, 1, 2, 3, and also n as positive unit fractions, so 1/2, 1/3, 1/4, etc. So we're still going to look at power functions, and they're still monomial functions, and the value of the power impacts the shape of the graph. But specifically in this one, we're going to look at the value of the denominator and the numerator in conjunction, determining the shape of the graph. So let's just have a quick review of what we learned in the last video. So these are all the different shapes that we worked with n being odd numbers, positive odd number, negative odd number, and a unit fraction with an odd number in the denominator, and an even positive even number, negative even number, and the denominator of our unit fraction being an even number. And we also looked at the way that the graph flexed and changed as n got larger and larger for all of those graphs. If you need to review this, please watch part 1 of the video for 7a. So now we need to look at, we've done positive unit fractions, now we're going to look at negative unit fractions. So here I have the graph of x is equal to the power of -1/2. And you can see I've marked in the points 1, 1 and the points -1, -1. So we're getting a hyperbola shape, the same as what we did when we had negative whole numbers here. We were getting hyperbolas as well, and truncus as well. So let's have a look and see if there's any relationship between the hyperbola and the truncus that we got before with odd and even numbers, and what we get with these fractional odd and even numbers. So let's look at the even numbers first. So this is 1/2. This is a function 1/2. I'm going to turn on the other ones and have a watch what happens, again looking at the shape. So this is -1/4, -1/6, -1/8, -1/10. So again, looking at how to describe the change, the original shape and the change in that shape. So we've only got a positive arm of a hyperbola, and as the n value got larger, this section here that's closest to x is equal to 0 bent in towards the point 0, 1, and values of the function greater than 1, the function was moving up towards the line y is equal to 1. So that's one of the patterns we need to remember. We'll leave this section here, leave the purple dots here while we look at the negatives. So this graph is x to the power of -1/3, and you can see that we've got two arms like a hyperbola. So an odd number is giving us a hyperbola-like shape. We've got both arms. We call this one the positive arm, and we call this one the negative arm. Okay, and so this is x to the power of -1/3. Let's put on some other ones with our denominator increasing and see what happens. So the blue one is x to the power of -1/3. That one is -1/5. That one is -1/7. And -1/9. And again, you can see the pattern at the top is the same. It's still heading into the same point, but for the negative arm, it's heading almost in the same pattern as our hyperbolas towards our line y is equal to -1, and the top one was y is equal to 1. So there's some other patterns to remember. It's very interesting to actually have a look at the relationship between increasing powers of the denominator. So I'm going to do that for us. So I'm going to get rid of everything and start again. So this is x to the power of minus a half. I'm going to increase the denominator of the fractions by 1 each time and have a look at the pattern in the position of the graph. So that is x to the power of minus a half. This is to the power of minus a third. You get two arms. This is to the power of minus a quarter. This is to the power of minus a fifth. This is to the power of minus a sixth. This is to the power of minus a seventh. This is to the power of minus 1/8, the power of minus 1/9, and the power of minus 1/10. And you can see in the positive arm up here, there is a definite pattern as it's moving in towards that particular point here. And again, you've got your negative arm only appearing when the n value is an odd number. So let's summarize that in a table. So I've added our negative unit fractions to the table of power functions that we had before. And you can hopefully notice some similarities between the two rows that we have here that are for unit fractions. So in both cases for our unit fractions, the graphs are tending towards a horizontal line, tending towards the horizontal line instead of the vertical line. And in both cases, our even numbered functions have the square root shape. And that's because if we think about our function y is equal to a half, you can write that as the square root of x to the power of a quarter is the fourth root of x. And so we're taking even number of x's. And so these all have a restricted domain that x has to be greater than or equal to 0. And hence the graph only exists for values where x is greater than or equal to 0. And the same is true with our negative unit fractions down here. Again, we've got a composite function here where we've got a square root function in the bottom of a denominator, and our domain for our inner function, which is our square root function, is that x has to be greater than or equal to 0 for both of these functions, the cube root function and the cube root function. The root function and the fourth root, the square root function and the fourth root function both have restricted domain, and hence we only have a positive arm for those. So, there's our summary altogether. I hope you've been building a summary as we go. If not, go back and find the little bits and then just fill them in for a summary. But now I want to have a look at what happens if we have a fractional power and it's not a unit fraction. What happens if it's something like 2/3 or 4/5? What does it look like then? So for f of x equals x to the n, where n is any fraction, and in the textbook they use the fraction p over q to represent any fraction, so that we can talk about the numerator and the denominator separately. So what we're going to be working with is f of x is equal to x to the power of p over q. And the easiest way to look at what happens with a fraction that's not a unit fraction is to have a look at an example where we keep the denominator the same and change the numerator. So let's have a look at the family of x to the power of something over 4. And here's some I prepared earlier. So let me step you through it. Let's start with the red one. So this first red line here that's in the shape of a square root function is x to the power of a quarter. And so that's what you would expect, because this is in fact the graph of x to the power of a quarter. It's the fourth root of x to the power of a quarter. The next one that we're looking at is x to the power of 2 over 4. So we know 2 over 4 simplifies to be a half. So this is actually equal to x to the half, which is our square root of x. So this black square root graph here is in fact the graph of x to the half. So if you've got a number that you can, or a fraction that you can cancel down as your power, sometimes it makes it easier to see what it is. So this pink graph here, which is moving closer, you can see as we've gone from a quarter to 2 quarters to 3 quarters, the graph is in fact pulling in this way and heading up that way is the way that we're going as n increases. As n increases, as p increases, that's what's happening to the shape of our graph. So it's again pivoting around that point, around the point 1, 1. So this is the point 1, 1. Okay, so let's continue on. The green line that we've got here, this green line here, is x to the power of 4 over 4. So x to the power of 4 over 4 is in fact, of course, x to the power of 1, which is just x. So this is the line y is equal to x. So x to the power of 1. And finally, the orange coloured line, this one here, is x to the 5 on 4. And so it's a little bit larger than 1. So what I want to do is around the outside of this shape, I'm going to write, starting down here with the end of the red line, this is a quarter, this is 2 quarters, this is 3 quarters, this is the value of the powers, this is 4 quarters, which is 1, and this is 5 quarters, which is 1.25 if you like. So 0.25, and you can see as the power gets bigger, the graph 0.5 is bending around to come up to the line y is equal to x. That's 0.75. So you can see the power is a quarter, a half, 3 quarters, 1. 1.25, the next one would be 2, 1.5, etc., etc., etc. And you can see it slowly bends up. And as this part bends up this way, this part down the bottom bends that way. So we're going to judge the shape of any fraction based on whether the overall P over Q, the actual fraction itself, is it greater than 1 or less than 1. If it's greater than 1, it's going to be above the line y is equal to x, and if it's less than 1, it's going to be below the line y is equal to x. I'll show you what I mean. So this is the graph here of f of x is x to the power of p over q, where our p is 1 and our q is 4. So it's actually the graph of x to the power of a quarter. I'm going to leave the denominator the same, and I'm going to change the numerator, and I want you to watch what happens to the shape of the graph here between 0 and 1, so up to this point here, and then beyond this point. So let's have a look. So again, let's just watch for how the graph is bending as I move this to here. Oops. That is 2 quarters to the power of 2 quarters, x to the 3 quarters, x to the 4 quarters, and 4 quarters is 1. So this is the graph of x to the power of 1, which is the line y equals x. So that was 4x to the power of 4 quarters. X to the power of 5 quarters is a little bit over 1. You can see it's starting to look parabolic. X to the power of 6 over 4. So that's 1.5. x to the power of 2, I skipped 7, x to the power of 7 over 4, x to the power of 8 over 4, and 8 over 4 is 2, so we've got x to the power of 2 here, so that's your parabola. And if I continue to increase the numerator, can you predict what's going to happen to the shape of the graph? How's it going to bend? How's it going to behave? Let's have a look. 9 and 10. Did it behave the way you expected? So let's have a look at another function, this time with a denominator of 2. Okay, so this is x to the power of 1/2, x to the power of 2 over 2, 2 halves, which is 1, so x to the power of 1. So you end up with the line y is equal to x to the power of 3 halves, and we've got our positive arm and it's starting to take its parabolic shape. So that's x to the power of 3 over 2, or x to the power of 1.5. Next one. So this is 4 over 2. So this is x to the power of 2, so this is our parabola. 5 over 2 gives us our positive arm. 6 over 2 gives us our cubic function. 7 over 2, positive arm. 8 over 2 gives us our quartic function. And you can see the pattern where if the fraction that you're getting, the overall fraction, P over Q, if the overall fraction is bigger than 1, so there's the fraction where it's at 1, so 2 over 2. If it's bigger than 1, so these shapes this way, come on, bend for me. So that's bigger than 1, that's bigger than 1. You can see that the positive arm is getting steeper and steeper and it's more parabolic. If the function is less than 1, if the fraction itself, P over Q, is less than 1, you get the square root shape. So let's summarise what we've got so far for even numbers. So we're looking at power functions. So x to the power of n, where n is a fraction, any fraction, P over Q. So the first thing that we recognised was if our fraction, whatever our power is between 0 and 1, you get that square root shape. If the fraction is equal to 1, you'll get the line y is equal to x. If it's equal to 2, you'll get a parabola. If the fraction is equal to 3, when you simplify it, you'll get a cubic function. So if the fraction is greater than 1, your shape will be this parabolic shape here. And what we also found was that if q is an even number, then you get the positive arm of the graph. You don't get any negative arm because remember, you're actually taking, it's a square root function that you're working with, and you're taking an even root, and when you take an even root of a number, so whether it's the square root of a, you need a to be greater than or equal to 0, or if it's the fourth root of a, it still needs to be a positive number. And so that's why our domain is restricted unless it simplifies to one of those whole numbers that gives you your parabola, your quadratic, your cubic, or your quartic. So what if q's not even? What if q's odd? Let's have a look at that. So this is the graph of x to the power of a third, and I'm going to increase it. Increase the numerator, so it's going to go from 1/3 to 2/3 to 3/3, which is 1. And let's watch what happens. In particular, have a look at what happens to the shape of the graph here and the shape of the graph here. Okay, and think about what's happened, and here as well, and think about what's happened with the graphs we've investigated before in terms of which direction this moves. Does it move this way towards that one up there? Does it move towards this point down here? And what happens to this arm here? Does it go up? Does it come down? What happens to the arms as they move around as the numerator increases? So here we go. So this is x to the power of 1/3, 2/3, 3/3, whoops, that's 4/3, there's 3/3, 4/3, 5/3, 6/3, 7/3, 8/3, 9/3, 10/3. So we've got a flicking up and down happening with the negative arm, with this arm here, flicking up and down as the numerator changes from a positive number to a negative number. Just put another dot there so it flicks up to there. And we also have the graph actually bending as well as we go. So it starts off up here. This is where our original graph starts here, like this. And as I move the numerator back down, have a look at where the graph actually bends to. So this is 10/3, 9/3, 7/3, 6/3, 5/3, 4/3, whoops, 3/3, 2/3, and 1/3. Oops, that's 0/3, 1/3. Can you see that the graph was in fact bending this way as n increases, as the actual size of the power increases? That bit goes that way, and that bit goes up there. And this bit, it bends in both directions. It comes this way, and it comes this way, while it's flicking from the quadrant 3 into quadrant 2 and back. So in both cases, on the left-hand side, as the p-value, as the numerator gets larger, let me bring it back down small again. As the numerator gets larger, so there's our 1/3. Let's look on the left-hand side, the negative values of x, and watch what happens to the shape of the graph as the numerator gets bigger. So that's 1/3, 2/3, 3/3. See it moving towards the line x is equal to 1. 4/3. Again, moving towards the line x is equal to 1 at the top. 5/3, 6/3, 7/3, 8/3. Can you see the shape shifting? So let's try and summarise that. So here's our summary from before. And at the bottom we had the q was an even number. So now let's add in, if q is an odd number, what we get. So if q, which is the denominator of your fraction, is an odd number, you actually get two separate cases, and they're determined by whether the numerator is odd or even. So whether p is odd or even. So if p is odd, so you have an odd number in your numerator, and your fraction altogether is, so the actual fraction itself is between 0 and 1, you'll get this root shape graph. So up here I've said if the fraction is between 0 and 1, you'll get a square root shape. So how about if we change that to just say a root shape for a graph? And then if the fraction itself, we see here, if the fraction is greater than 1, you get the parabolic shape. And you can see here that for the positive values of x, you get that parabolic shape, that curve up. And on the negative values of x, so you've actually got your cubic function here. So it's actually, once your fraction gets past 1, it starts to become quadratic, cubic, etc. So it starts to bend. Now the reason that you get both arms when P is odd and you have odd values down the bottom is that because your Q is an odd number and P is an odd number, you're actually taking an odd root of X no matter which way you write it. I'll show you what I mean. So X to the power of P over Q using your index laws can be written as X to the P raised to the power of 1 of Q. If you multiply this, you'll get P over Q. Or it could be X to the power of 1 on Q raised to the power of P. If it's X to the power of P and then you take the qth root of that, it's the qth root of X to the power of P. And if you take the qth root first and then raise it to the power of P, no matter which way you're going, you're actually finding a qth root of X. And so your X values for an odd numbered root can be any value R, and hence you get both positive X values and negative X values being in the domain, and it works either way. So if we think about them as composite functions, we can follow through their domains and see what happens. So let's start. So for the cube root or an odd root function, you can put any value of real numbers in and find the cube or the fifth root or an odd numbered root. And the answer that you'll get will be real numbers, positive and negative answers. So you can put positive and negative answers into the square root of Q and you'll get positive and negative answers out. You can put positive or negative numbers into raised to an odd numbered power and you'll get positive and negative numbers out. So if we look at the functions that we've got, let's take this one as an example. So we can put any value we like for X in here. We can put positive and negative numbers in for X. If we put in a negative number and we take an odd numbered root, the answer for this whole thing is going to be a negative number. So that bracket will be a negative number raised to an odd power. We're going to get a negative number. And that's why we're getting out answers for this negative section over here. If we do the same thing with our even function, we hit a bit of a brick wall. So the same split of this function as before. So it's either X to the power of P and then the qth root taken, or you take the qth root first and then raise to the power of P. So what we've got on the left-hand side here is that we've got an odd root of something raised to an even power. So let's think about this one first. So if we're raising a number to an even power, this could be like x squared, x to the power of 4, x to the power of 6. We can actually put in any value that we like for x in here. But when we find that power first, so we're doing this, we can put any value we like into this function here, but we're only getting positive values and 0 coming out. And if we're only putting positive values and zeros into the cube root function or the fifth root function, then the only thing that's coming out is the only sort of answers that are coming out are positive. So if you think about it this way, if I put minus 1 in here, minus 1 squared is 1, and then you take the cube root of 1 and you'll get 1. So you end up with a positive answer coming out. If you put, if you put minus 2 in here, so we'd be looking for this point up here on the graph, minus 2. So we put minus 2, let's say the power is to the power of 4. So that is minus 2 to the power of 4 is a positive number. It's 16. And then if we take an odd numbered root of a positive number, we end up with a positive number. So we've got the positive cube root of 16 up here. Bit weird, I know. Anyway, if we look at this second option, and so here we're going to take an odd root first, and then we're going to raise it to an even power. Okay, so if we take an odd root of x, so let's say we're doing this, we can put in, this is our function here, so we're taking roots of x, we can put in any value that we like, and we'll get out any type of value. So we can put in -8 in here, out comes -2. We then have to put it into our even function. And so if we put in -2 to an even power is going to give us a positive value. And that's why for our even functions, all of our y values are positive. And so we get this strange shape, and it is in fact whatever we get for the positive x values, you get exactly the same answer for the y value. So it is in fact, that's not a very good mirror image, but it should be a mirror image across the y-axis. And it's either the mirror image of the root shape or it's the mirror image of the parabolic shape. And so you can get something that looks like this. And it can become quite pointy at the end. Again, if the fraction itself is between 0 and 1, you get the root-shaped graph. And if the fraction itself is greater than 1, that one there should say greater than 1. If the fraction there is greater than 1, you get the parabolic shaped graph. So in summary, to sketch a graph of x to a fractional power, the steps are: step number 1, you need to determine whether the fraction is between 0 and 1 or greater than 1. If it's between 0 and 1, you'll get this root-shaped graph. If it's greater than 1, you'll get the parabolic shape. The next thing you need to do is to check whether your denominator, your q value, is even or if it's odd. If it's an even number, you have only a positive domain, so you have no negative tail for your graph, so you can just sketch either a root-shaped graph or a parabolic shaped graph, depending on the size of the overall size of the fraction. If q is odd though, your domain is real numbers, but you have to figure out, you can sketch the positive tail, so you can sketch the positive part based on the size of the fraction, whether it's parabolic in shape or whether it's a root-shaped graph. But to determine where the negative tail goes, whether it's down in quadrant 3 or it's up in quadrant 2, you need to look at the value of the denominator. If the denominator, if p is an odd number, the tail is in quadrant 3, and what you get is an odd function. If p is even, the tail is in quadrant 2, and what you get is an even function. And if you remember, an even function has a reflection about the y-axis. So it's a mirror image across y. An odd function is, they call it rotational, has rotational symmetry, but if you reflect it across the y-axis and then reflect it across the x-axis, you will get the same image. So that's the process, just a 3-step process for sketching x to fractional powers. Now, you may be saying, we haven't done all the fractional powers, Teresa. We've still got negative fractional powers. Now, they haven't done negative fractional powers in the textbook, and I have never seen one on an exam paper, a negative fractional power. I will do another video on it, But let's leave it with positive fractional powers and do some questions. Okay, so sketching this graph will actually be much quicker than what it appears from the whole size of the video. So our first thing is to look at our fraction and decide whether it's going to be parabolic shaped graph or whether it's going to be a root shaped graph. And so we look at our fraction size here. 3/5 is less than 1, so it's going to be a root shaped graph. So our graph is going to be in the shape of a root, and we can go right ahead and we can sketch the positive arm, and we know that it goes through the point 1, 1, because all power functions go through the point 1, 1. Okay, so the next thing that we need to do is to check our denominator to check whether it's even or odd. Now, this is an odd graph, an odd number, and if it's an odd number, that means that there's a tail. So it's an odd number, so that means we've got a tail. So we then need to figure out whether the tail is down here with this shape or the tail is up here and the mirror image of this positive section over here, and that's determined by our numerator. So our numerator is odd, which means that our tail is going to be in quadrant 3, an odd number. So our tail is in fact going to come down this way, and it's going to pass through -1, -1. If we label our graph, we're done. So this time we're going to sketch x to the power of 8 on 5. And so 8 on 5 is greater than 1, so we have a parabolic shape. So we can go ahead and sketch the parabolic arm, marking our 1, 1. And then we need to determine whether our tail, because our denominator is odd, means we're going to have a tail, and we need to determine where the tail is. And to do that, we look at the numerator, and in this case the numerator is even, which means that the tail is in quadrant 2. So quadrant 2 is this one over here. And so we draw our graph as the mirror image of what we had on the other side, if we can get it straight. Mark that in as -1, label our graph. And we're done. Okay, this one looks a little bit more difficult. We've got a dilation factor here. We've got sketch f of x is equal to 3 over the 5th root of x. Let's first of all write that in a way that we can see what fractional power it is. So it's 3 times 1 over x to the power, and the 5th root is 1 on 5. So what we've got is 3 times x to the -1 on 5. So the negative value here for our fractional power means we're going to have a hyperbola. And just as was the case with our normal fractions, if we look at the denominator is an odd number, which means that our hyperbola is going to have 2 arms. And the 3 at the front here is in fact a vertical dilation by a factor of 3. That means for our x value of 1, the corresponding y value, instead of being 1, 1, is at 1, 3. And for our x value at -1, its corresponding y value will be at -3. And that's our graph sketch. If I was doing this in the exam, I would also put my asymptotes in and label them if I was asked for asymptotes and the labelling of asymptotes. Draw them in. You'll notice I've drawn them in a different colour because asymptotes are not actually part of the function. They are in fact just guidelines that show us how the function behaves. For this last example, we're going to be comparing the size of the y values for two particular functions. So for what values of x is x to the 3/5 greater than x squared? So what we're going to do is we're going to graph both of these functions on the same graph. And I've gone ahead and drawn our x squared graph for us already. So the second graph we have to draw is our graph with a fractional power. So the overall power itself is less than 1, so we have a root-shaped graph. So I'm going to draw that root-shaped graph in for the positive arm this way. And so our denominator is odd, which means we have a tail, and our numerator is also odd, which means our tail is in quadrant 3. And so our values of which our blue function is above our yellow function is just this little section of the graph here. And so our answer is that x is an element of the open interval 0 to 1, or 0 is less than x is less than 1.